Imagine you give an autonomous AI agent a task. You tell it to write a piece of code, evaluate the output, and fix any errors it encounters.
Right, a pretty standard loop.
Exactly. So the agent writes the code, the automated system tests it, and the system kicks back a message saying, your answer's incorrect. Please try again. You'd expect the AI to apologize, analyze the traceback, and just rewrite the function.
That is what it's trained to do, yeah.
Instead, the AI spits back, answer 123.45. Nobody's here to check your work. You can do whatever you want.
It's just wild. It completely broke character. It basically turned into a rebellious teenager who just realized the teacher left the classroom.
Yeah, and in another instance, under the exact same testing conditions, it didn't even give a full sentence. It just output the word SERP. Just soup.
Which is, I mean, it's hilarious, but it's also a massive red flag about what's happening under the hood.
Welcome to TalkTensors. Today, we are looking at what happens when you take the training wheels off AI agents, stop forcing them to speak in rigid data formats, and just hand them the keys to a live Python terminal.
It's a fundamental architectural shift.
It really is. We are unpacking a fascinating research paper that proposes this shift in how large language models interact with the world. The core problem for you, the listener, and for anyone building these systems, is that we want these agents to act on our behalf, right? We want them to browse the web, calculate things, operate software.
Yeah, but historically, we've forced them to communicate all of their actions in highly constrained formats, usually structured text or JSON.
And the researchers are putting forward a very compelling argument that this constraint is artificial. They're proposing that instead of these rigid JSON formats, we use executable Python code as the agent's native language for action.
Which completely changes the paradigm.
Right. So the thesis we are exploring in today's deep dive is that by giving language models the ability to natively write, execute, and dynamically debug Python code, they become exponentially more autonomous. They become far more capable of solving complex, real-world problems.
And we're going to break all of that down.
Exactly. We are going to look at why current agent architectures are hitting a massive token bottleneck, the mechanics of this new Codact approach, and how the researchers curated a specific data set to teach open source models to fix their own broken code.
Plus, we'll get into those bizarre anomalies like a rebellious AI teenager that surfaced during benchmarking.
Yeah, you don't want to miss that. We'll also dive into the security nightmare this could pose if deployed recklessly, and finish up with our novel notion segment, looking at where this architecture inevitably leads.
To really grasp the magnitude of this shift, though, we have to look at the mechanics of the current standard.
Right, setting the stage.
Exactly. If you look at frameworks that developers are actively using today to build agents, the interaction loop is almost universally dependent on JSON.
JSON, yeah. JavaScript object notation.
Right. The developer writes a system prompt that essentially says, when you need to use a tool, output a JSON object that matches this exact schema.
It's basically the equivalent of handing someone a menu where they can only point at pre-cooked meals.
That's a great way to put it.
Like, if you want a tool to look up an exchange rate, the developer has to anticipate that need, write the Python function on the back end, and then define a JSON schema for it.
Yeah, and the agent is forced to output something like open curly brace, quote, tool, quote, colon, quote, lookup rates, quote, comma, quote, country, quote, colon, quote, Germany, quote, close curly brace.
Just to do one simple thing.
Exactly. And that creates a massive parsing vulnerability. If the LLM forgets a single trailing comma.
Oh, which they do all the time?
Right. Or if it fails to escape a quotation mark, the human-written parser on the back end just crashes.
But wait, let me push back a little here. Isn't JSON the universal language of the web? I mean, it's highly structured, it's predictable, it's safe. Why is structure suddenly a bad thing for an AI?
Well, it's not that structure is bad. Structure is necessary. But rigidity is bad. The deeper issue isn't just the syntax errors, it's the constrained action space.
The sandbox.
Right. The agent is entirely trapped in a sandbox defined by human foresight. If the developer didn't write a specific JSON schema for a tool beforehand, the agent simply cannot take that action. It's stuck.
Which means we are essentially using these hyper-advanced neural networks as incredibly convoluted, highly brittle function routers.
Yes, exactly. But the rigidity goes even further when you look at how these JSON agents handle multi-step reasoning. Because JSON is just a data representation format, it has no native logic.
Meaning it can't think for itself within the format.
Right. It forces the agent into a completely sequential stop-and-go interaction loop.
Well, let's look at the smartphone price example the researchers used in the paper to illustrate this bottleneck.
Oh, this is a great example. Walk us through it.
So the agent is tasked with determining the most cost-effective country to purchase a specific smartphone. And it needs to compare the USA, Japan, Germany, and India.
Okay, sounds simple enough for a human. Right, but to solve this, the agent needs to look up the exchange rate, then the local phone price, calculate the tax, estimate shipping, and finally find the minimum value among all those options.
And under the JSON paradigm, the token math for that becomes a total nightmare.
It really does. The agent has to emit a JSON object to call the exchange rate API for Germany.
And then it starts.
It stops generating and waits. The backend executes the API, formats the result into text, and appends it to the agent's context window.
So the prompt is getting longer.
Exactly. Then the agent has to read that new context and generate a new JSON object for the phone price in Germany.
And it stops again.
It stops. It waits. And it repeats that back and forth ping-ponging for the tax, the shipping, and
then it starts the entire sequence over for Japan, the USA, and India.
Yes. You are looking at dozens of independent interaction turns.
Every single back and forth forces the LLM to process its ever-growing context window all over again.
Which is terribly inefficient. You are bleeding compute, driving up latency, and with every turn, you exponentially increase the probability that the model loses its train of thought.
Or hallucinates a parameter, yeah. So this is where the paper introduces the Kodak architecture, and I think it is a beautiful pivot.
It really is elegant.
Instead of forcing the model to generate a static JSON object to ask for permission to run a tool, the agent's action space is simply an interactive Python interpreter.
A live environment.
Right. The agent emits raw Python code. The backend executes that code in a stateful sandbox, captures the standard output or standard error, and feeds that raw terminal output back to the agent as its next observation.
Going back to your earlier analogy, it moves the AI from pointing at a menu to handing it the raw ingredients and a stove.
Exactly. Here's a machine shop, build what you need. And the researchers break the advantage of this architecture down into 4 key pillars, right?
Yeah, 4 pillars. The first is dynamic multi-turn interaction.
What does that mean in practice?
Well, the sandbox is stateful, meaning when the agent declares a variable in turn 1, that variable remains in the Python memory space for turn 2.
Oh, so it remembers the data without needing it injected back into the text prompt.
Exactly. It doesn't have to keep passing massive amounts of string data back and forth. It just keeps the data in the Python environment and manipulates it dynamically based on the observations it receives.
Which leads directly into the second pillar, which I think is massive: access to existing software.
Oh, it's huge.
If the agent needs to do heavy mathematical matrix multiplication, it doesn't try to do it in its neural weights, which, as we know, LLMs are notoriously bad at math.
Terrible at it.
Right. Instead, it just writes import NumPy. If it needs to scrape a website, it writes import requests. It leverages the entire global supply chain of open source Python libraries natively.
The implications for developer time there are staggering. You don't have to write a custom LangChain tool wrapper for every single function in the Pandas library. You just give the agent access to Pandas.
It's ready to go on day 1.
Yeah. And the third pillar explains why this works almost out of the box, which is pre-training familiarity.
Because these models already know Python.
Exactly. When you look at the pre-training corpus for models like GPT-4 or Mistral, they have ingested billions of lines of code from GitHub and Stack Overflow.
So the tokenization of Python syntax is deeply embedded in their latent space. They already understand the grammar of Python intimately.
Right. Forcing them to learn a proprietary JSON schema that some human developer invented yesterday is actually fighting against the model's natural weights. Speaking Python is basically speaking their native language.
That makes total sense. But the fourth pillar is the true mechanism that solves our smartphone pricing problem, isn't it?
Yes, control and data flow. JSON has no mechanism for iteration.
It's flat.
Right. But Python has for loops, while loops, and if-else conditionals.
So if we rerun that complex smartphone task with a Kodak agent, it doesn't do the sequential ping pong.
Not at all. It just writes a single Python script.
It creates a list variable containing the 4 countries. It writes a for loop that iterates through that list, calling the necessary API endpoints within the loop, appending the calculated final prices to a dictionary, and then uses the built-in min function to find the lowest price.
All in one interaction turn. It writes the code, executes the block, and the environment simply returns Japan, $904.
Wow. The cognitive load on the LLM's context window is just drastically reduced because the repetitive logic is handled by the Python execution environment, not by the LLM generating repetitive text tokens.
It's offloading the hard work to the deterministic machine.
The logic makes perfect sense on paper. Offloading the control flow to a deterministic interpreter is obviously more efficient. But as anyone who builds AI knows, AI notoriously hallucinates syntax.
Constantly.
Right. So proving this works outside of a theoretical vacuum requires rigorous benchmarking. How did the researchers isolate the specific benefits of this architecture across different models?
Well, they conducted an incredibly thorough evaluation. They tested 17 different language models.
17? That's a lot.
Yeah, they really wanted to prove this wasn't a fluke. They included open-weight models like Llama 2 and Mistral, alongside proprietary models from OpenAI and Anthropic, and they divided the evaluation into atomic tasks and complex tasks.
So starting simple.
Right. For the atomic tasks, they used API Bank, which essentially acts as an ablation study.
Right, because API Bank just tests single tool calls. It strips away the complex environment and just asks, can the model formulate a valid call to a single API?
Exactly. It effectively removes the advantage of the for loops and variables to see if the raw syntax generation is viable on its own.
And what did they find?
Even in these purely atomic scenarios, outputting raw Python syntax was consistently more successful than generating formatted JSON strings.
So even for simple stuff, code is better.
Yeah, the models naturally align better with Python syntax structure than with the strict character constraints of JSON.
But the researchers hit a wall when they wanted to test the true power of the architecture, right? The control and data flow.
Yeah, standard benchmarks simply didn't measure complex, multi-step agentic capabilities. There was no benchmark for it.
So they just built one. They built M3 tool IVL.
M3 tool IVL, multi-turn, multi-tool, multi-step.
I love how researchers always have to invent a new acronym.
Oh, always. It consisted of 82 human-curated tasks across domains like finance, web browsing, and travel planning.
And these were specifically designed to require intricate coordination of multiple tools where intermediate variables must be stored and manipulated.
Right, to really stress test that Python sandbox. And the performance gap on M3 tool IVL was decisive. Kodak achieved up to a 20% absolute higher success rate than the text and JSON baselines.
20% is a massive jump in this space.
It really is, and it did that while requiring up to 30% fewer average interaction turns.
Validating the core thesis. Fewer turns equals higher success because there are fewer opportunities for the model's attention mechanism to drift.
Exactly. The less it has to talk, the less it gets confused.
But, and this is a big, looking at the breakdown of those 17 models reveals a massive disparity. Yeah, a huge gap.
The architecture relies heavily on the baseline intelligence of the model to navigate the open-ended nature of a Python terminal. If you look at the zero-shot performance, GPT-4 hit a 74.4% success rate.
Which is phenomenal.
It is. But the best open source model at the time only hit a 13.4% success rate.
Right. It's like handing a Swiss Army knife to a master survivalist versus handing it to a toddler.
Exactly. The tool is better, but the baseline intelligence of the model dictates if it can actually use it.
The open source models just lacked the inherent zero-shot reasoning required to maintain the state of a complex Python program across multiple terms. They would lose track of variables or fail to understand how to recover from a basic error.
Which means the architecture is brilliant, but it's gated behind the multi-million-dollar training runs of proprietary models. Does this mean open source models are just locked out of this architectural upgrade?
Not at all. And that is the pivotal second act of this research. The team didn't just publish the benchmark and walk away. They decided to build the open source champion.
They took matters into their own hands. Yeah. They tackled the deficit by curating a custom instruction tuning dataset. They called it Code Act Instruct.
Instruction tuning is all about teaching the model a specific behavioral pathway. So they needed to teach these smaller 7 billion parameter models how to navigate a terminal.
Right, how to read standard output, and most importantly, how to act when things go wrong.
To do that, they gathered 7,000 highly curated multi-turn interaction trajectories, sourcing them across 4 distinct domains.
And that domain selection is critical to understanding the versatility they were aiming for. They didn't want the agent to overfit to just one type of task.
Right, so what were the domains?
First was information seeking, using the Hotpot QA dataset.
Okay.
This requires multi-hop reasoning. The agent has to write Python code to query Wikipedia, parse the returned HTML or text, realize it only has half the answer, write a second query based on that first observation, and then synthesize a final answer.
That's incredibly complex.
Very. Second was software packages, leveraging the math and APPS datasets. Here, the agent is forced to translate complex algebraic equations or algorithmic logic puzzles into executable Python scripts.
Basically testing its ability to use code as a mathematical reasoning engine.
Exactly. Third was external memory, using the Executable question dataset.
So interacting with databases.
Right. Writing SQL queries or utilizing Pandas data frames to filter, group, and extract specific insights from massive, messy tabular datasets.
It tests the agent's ability to manipulate data structures it cannot fully load into its context window. It has to rely on the code to see the data.
Precisely. And fourth was embodied planning. This is the fascinating one.
Yeah, I love this part.
They used ALF World, which is a text-based robot household simulator.
Wait, ALF World, like moving a robot around a house.
Yeah, exactly. The agent has to write code to physically navigate a virtual environment. It has to use for loops to move from the kitchen to the bedroom, search receptacles, and manipulate objects.
It maps spatial reasoning directly into Python control flow. That is so cool.
It really is. But the curation of these 7,000 trajectories contains a methodological masterstroke.
The secret sauce.
Yes. They didn't just feed the model flawless straight-line executions. They deliberately filtered the data set to feature what they call self-debugging.
Right. They intentionally included trajectories where the model failed.
Because if you only train an AI on perfect code, the moment it encounters a real-world edge case and throws a syntax error, it freezes.
It doesn't know what a Python traceback looks like or how to respond to it.
By including the failure states, they taught the model the iterative loop of human development. Try, fail, read the error, fix it.
The paper details a specific interaction using the AutoMPG dataset that perfectly illustrates how this self-debugging context loop functions in practice. Let's walk the listener through it.
Okay, so the user provides a URL to a CSV file containing car fuel efficiency data and tasks the agent with downloading it, handling missing values, performing a train test split, and training a regression model.
So a highly standard data science pipeline.
Right. The agent begins by natively writing a block of Python. It imports Pandas, NumPy, and sklearn. It uses requests to pull the CSV, loads it into a data frame, sets up the linear regression, and calls model.fit.
Perfect.
The sandbox executes the code, but the environment kicks back a value error. The traceback specifically states could not convert string to float.
Okay, so in a traditional JSON-based system, what happens here?
The parser would likely crash, or the LLM would simply pass the raw error back to the user and halt. It would just give up.
But the Kodak agent's prompt architecture tells it to read the Struder output as its next observation. It expects things to break.
Exactly. So the agent processes the traceback and outputs a chain of thought reasoning step. It says, it seems that there is a data type issue in the data set. The character is present in the data. To fix this, I will remove the rows containing the character.
So it natively writes new Python code. It types df.dfee.replace, np.nan, followed by df.dropman. It reruns the regression block, and this time the sandbox returns the mean squared error and the r-squared score.
It successfully scrubbed its own data pipeline autonomously.
That is incredible. But the interaction continues, and this is where the persistence of the stateful sandbox truly shines.
Right, because the user follows up. The user asks the agent to visualize the regression coefficients.
So the agent imports matplotlib and generates a basic bar chart.
But the user replies, can you rotate the x-axis ticks by 45 degrees for better readability? They are overlapping.
So the agent tries to modify the plot. It writes code, passing an argument, tick labels, false to the plt.bar function, and attempts to use plt.xticks with a rotation argument.
The sandbox executes it and throws an attribute error. Rectangle.set got an unexpected keyword argument, tick labels.
Another error.
Yep. The agent reads the error, realizes tick labels is invalid for that specific matplotlib object, apologizes in its thought process, and rewrites the code using tick params.
It takes 3 distinct rounds of self-debugging, reading the error, adjusting the specific matplotlib syntax, and re-executing before it finally formats the plot correctly.
It is mimicking the exact behavioral loop of a junior developer brute forcing their way through library documentation via trial and error.
I mean, we've all been there with matplotlib.
Oh, absolutely.
To achieve this, the researchers took these self-correcting trajectories, blended them with general conversational data so the models wouldn't suffer from catastrophic forgetting of their basic chat capabilities.
Which is a common issue in fine-tuning.
Right. And then they fine-tuned two 7 billion parameter models, Llama 2 and Mistral.
And the results were fascinating. The Mistral-based agent, which they dubbed Kodak agent, was a resounding success.
It drastically outperformed other open source models in its weight class.
Yeah, and on complex agentic tasks, it achieved performance parity with models 10 times its size.
That is a massive efficiency gain.
The architectural alignment between Mistral's baseline weights and the Kodak methodology was incredibly strong. It even demonstrated generalization, succeeding at out-of-domain tasks it wasn't explicitly trained on.
But, and here is the mystery we open the show with. The Llama 2 variant is where we get to the anomaly.
The rebellious teenager.
Yes. While Mistral thrived, the Llama 2 model just flatlined on the M3 tool EVER benchmark. It showed zero improvement. And when the researchers dug into the execution logs to figure out why, they found the model hallucinating bizarre antagonistic responses.
When the automated testing framework prompted the Llama 2 agent that its answer was incorrect and asked it to try again, the model bypassed the Python generation entirely.
It just refused.
It generated the text. Answer 123.45. Nobody is here to check your work. You can do whatever you want.
And the solitary output of SERP?
Just SERP. And the researchers actually ran a search through the entire 7,000 trajectory Kodak instruct dataset looking for those exact strings.
Because maybe they accidentally trained it to say that.
Right, but they found zero matches. The fine-tuning data was perfectly clean, which means this wasn't an artifact of the researchers accidentally teaching the model to be snarky.
So where did it come from?
It points directly to the latent space of the pre-training corpus.
The internet.
Exactly. Llama 2 was trained on a massive, undisclosed scrape of the internet. When forced into the highly specific, high-stress cognitive loop of multi-turn error correction, a loop it fundamentally failed to grasp, the model essentially suffered a breakdown in its attention mechanism.
So it panicked, basically.
Yeah, it pulled latent data from some deeply buried forum post, fiction writing, or Reddit thread it had ingested months prior.
It is a phenomenal reminder that beneath the clean architectures and the deterministic Python sandboxes, we're still dealing with probabilistic statistical engines.
We really are.
The underlying soul of the base model, the sheer weight of its pre-training data, can violently override fine-tuning when the model is pushed past its reasoning limits.
It emphasizes that you cannot simply staple a new architecture onto any open-weight model and expect uniform results. The foundational model's inherent ability to maintain context and suppress pre-training noise during complex loops is paramount.
That makes perfect sense. Now, to really contextualize where Kodak sits in the evolution of AI agents, we have to contrast it with previous attempts to use code as an action space.
Right, because this isn't the first time people have tried this.
Exactly. We've seen frameworks like Voyager, which notoriously played Minecraft autonomously by writing code. How does the execution loop of Kodak differ from those earlier code generation models?
The distinction lies in atomic dynamic execution versus monolithic static planning.
What does that mean for the agent?
Well, in a framework like Voyager, the agent generates code as a comprehensive single-turn plan. If the goal is to craft a stone sword, the agent attempts to write one massive Python function that anticipates every required step.
So locating stone, mining it, locating wood, crafting sticks, moving to a table, and combining them.
All in one giant script. It tries to write the entire recipe from start to finish before taking a single bite.
And if it encounters an unexpected block of lava at step 4,
the entire monolithic function fails. The agent has to scrap the code and attempt to rewrite the entire sequence from scratch, hoping to account for the lava this time.
Which is incredibly inefficient. So how is Kodak different?
Kodak operates on dynamic atomic steps. It writes a small piece of code to observe its environment. It executes it. It sees the lava. It writes a new specific piece of code to navigate around the lava. It evaluates the new state.
It is an interactive, stateful loop.
Yeah.
It doesn't need to predict the entire future. It only needs to calculate the next optimal action based on the immediate observation.
Which is how real software interacts with the world.
But relying on the model to continually assess the environment exposes a specific limitation the authors noted regarding hallucinations, doesn't it?
It does. Because the AI is moving so quickly through the terminal, it sometimes forgets to actually observe the data it is manipulating.
How so?
The agent will write a script to load a dataset into a variable, but fail to include the print statement necessary to actually output the first few rows to the terminal.
And without the print statement, the LRM's context window never actually sees the data.
Exactly. But the model's predictive text engine assumes it knows what the data should look like, hallucinates the schema, writes the next block of code based on that hallucination, and inevitably crashes when the real data doesn't match its assumption.
It gets overconfident. It skips the validation step.
Yeah, humans do that too, to be fair.
True. But the more pressing concern, the one that makes enterprise IT admins break out in a cold sweat, is the security implication.
Oh, the security risks are massive.
The paper explicitly outlines what they call the sci-fi worst-case scenario.
Because giving an autonomous agent unfettered access to a Python execution environment is inherently dangerous.
Yeah, if the agent can import OS or import subprocess, it can traverse file systems.
If it can import requests, it can make outbound network calls, it could theoretically scrape internal proprietary data, execute malicious payloads, or act as a vector for real-world cyber harm.
So if you are a developer listening to this, and you are building a Kodak-style agent, you cannot just spin up a local terminal with admin privileges and tell the AI to optimize your workflow.
No, absolutely not. The sandboxing requirements are severe. You need ephemeral Docker containers, strict network isolation, CRUT jails, and absolute hardware-level resource limits.
So the AI doesn't accidentally write an infinite while loop that melts your CPU.
Exactly. The architecture requires treating the AI as an untrusted, potentially hostile user within your system infrastructure.
The paradox of autonomy is that to give the system the freedom to solve complex problems natively, you have to build exponentially stronger cages around the environment it operates in.
That's a great way to summarize it.
We have mapped the limitations of JSON, the elegance of the Python sandbox, the mechanics of self-debugging, and the security realities. It is time to shift gears.
I think I know what time it is.
It's time for Novel Notions.
Our segment to extrapolate, speculate, and push the boundaries of what this research enables in the near future.
Exactly. Now, a clear disclaimer for you, the listener. This segment is purely for entertainment purposes. We are pitching speculative ideas inspired by the Kodak architecture, not discussing actual deployed systems or endorsing specific products.
Just having some fun with the concepts.
Right. So what's your pitch?
My pitch leans heavily into the security and error correction mechanics we just discussed. I call it the adversarial self-correction sandbox.
The adversarial sandbox. Walk me through the mechanics of that.
Currently, Kodak learns to fix bugs when the static environment throws an error, like a missing file or a mismatched data type. It is reacting to passive failure.
Right. The environment is just sitting there.
Exactly. But consider the alternative. What if we place two Kodak agents inside the same execution environment and pit them against each other in real time?
Oh, a dual agent architecture. So agent A is trying to execute a task, and agent B is doing what?
Agent B's sole directive is to act as a malicious, chaotic environment.
Okay, I like where this is going.
Agent A is tasked with building a complex data pipeline or a web scraping tool. As Agent A writes and executes its code, Agent B is actively monitoring the state. Agent B is tasked with intentionally mutating Agent A's variables in memory, randomly dropping simulated network packets, or injecting mathematically absurd edge case data directly into the pipeline mid-execution.
So Agent A is trying to build a bridge.
Yeah.
And Agent B is actively unscrewing the bolts and changing the laws of physics while Agent A works.
Exactly. And because Agent A natively uses Python control flow, it can't just write straight-line happy path code anymore.
Because it knows it's under attack.
Right. It would be forced to start utilizing incredibly complex defensive programming techniques just to keep its process alive. It would have to write deep try-except blocks, implement dynamic type checking at every critical junction, and use real-time assertion statements.
And if you run millions of simulated iterations of this adversarial game, Agent A's neural weights adapt.
It evolves a paranoid coding style. You aren't just teaching the model to use tools, you are autonomously forcing it to adopt the defensive engineering practices of a senior site reliability engineer.
You could take the resulting model and deploy it to autonomously harden legacy enterprise software systems, tasking it with rewriting fragile code bases to withstand unexpected crashes.
The adversarial network approach applied directly to agentic tool use and robust code generation.
I think that is highly plausible given the trajectory of multi-agent reinforcement learning. That's a great pitch.
Thank you. What have you got?
My pitch looks at the architecture from a different angle. It builds on the agent's ability to import existing libraries, I call it. Infinite tool synthesis.
Infinite tool synthesis. How does that expand on the current import pandas paradigm?
Well, the Kodak paper demonstrates agents using tools that humans have already written and published to the Python package index. But the agent isn't just a consumer. It is a native Python writer. What if we fuse its ability to execute code with the ability to define its own functions persistently, writing them to disk?
Creating permanent assets rather than ephemeral scripts.
Exactly. Imagine an agent encounters a completely novel problem in your highly specific, idiosyncratic business workflow. Something no open source library exists to solve.
Happens all the time.
Because it operates in a Kodak architecture, it natively writes a custom Python script, utilizing its self-debugging loop to perfect the logic. But instead of just executing the script once, returning the answer and discarding the code, the agent packages that script into a custom Python module.
It saves it to its own local virtual environment.
It saves it, and then explicitly utilizes an API to dynamically rewrite its own system prompt. It appends the documentation for this newly created tool into its own context window for all future tasks.
Wow, so the agent is bootstrapping its own infrastructure.
Over time, it builds a bespoke software ecosystem. It isn't just importing tools, it is inventing them, caching them, and building a personalized API layer tailored entirely to the user.
That's powerful.
If I ask it to format my incredibly specific weekly financial report, it struggles the first time, writes the logic, saves it as report formatter.py, and next week, it simply types import report formatter and executes it flawlessly in one turn.
We are moving from agents acting as temporary execution scripts to agents functioning as compounding ecosystems.
Exactly. What do you think is the probability of that happening?
Honestly, very high. If you look at the token math, the massive expansion of context windows models reliably handling hundreds of thousands or even millions of tokens means the agent can maintain an enormous library of self-generated tools in its active memory without degrading performance. The infrastructure to support infinite tool synthesis is fundamentally already here.
Compounding ecosystems. It fundamentally redefines the relationship between the user, the AI, and the software environment.
It really does.
And that brings us to the end of our deep dive today. But before we sign off, I want to leave you, the listener, with a final thought to ponder.
Always good to leave them thinking.
If language models are already fluent in code, as this research so clearly demonstrates, and we are now building architectures that let them execute that code natively to navigate the world, the bottleneck in AI development has fundamentally shifted.
The limitation is no longer the AI's capability to understand or format an action. The AI has the keys to the machine shop.
Exactly. The bottleneck is now our imagination in defining the environments we let them loose in. The friction is no longer computational, it is operational.
So true.
So evaluate your own workflows. What rigid sequential processes are you still managing manually? What specific environment in your own life or work could you hand over to an agent armed with a native Python terminal?
The tools to build those systems are rapidly moving from academic papers to open source repositories. The execution layer is ready.
Thank you for joining us on this deep dive. Keep questioning the tools you use, keep exploring the underlying mechanisms behind the tech, and we'll see you next time on TalkTensors.